The clearance 1 rule sets the clearance all the way down to 2.8 mil. Now that's a pretty aggressive clearance value. We can see here that we have a clearance requirement as a function of the weight that gets etched in the PCB on the surface layers and on the inner layers. So the minimum spacing value depends on two factors. Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today, we're gonna be doing a deep dive of a high density design from Amir Mohammed Ghanai. This is one of the designs that was sent in for the 1-minute design review series. And because it is a high density design, I thought it would be great to do a deep dive on this and see what we can learn about some of the common mistakes that happen in HDI boards. Now, we've done quite a few deep dives in the past. We've looked at power designs, we've looked at RF designs, and this is gonna be our first deep dive of a high density design. Now, high density designs can be difficult if it's one of your first designs, so hopefully some of the tips and tricks that we're gonna learn in this video will help you with your next HDI design. Now let's go ahead and jump right into this design from Amir Mohammed Ghanai. This design is an audio interface PCB that connects to a flex cable through a mezzanine connector, and then it also has a large battery cell, which we can see in 3D. So first, let's take a look at this board. Here you can see what it looks like in 2D, and then here you can see what it looks like in 3D. If I just zoom out and flip this over, you can see the top layer. Here you can see that mezzanine connector, or that high-rose connector, which connects to our flex cable. And then here we have what looks like just a big cylinder, but there are battery input ports on this design, and I would assume that this big cylinder is the coin cell battery. So before we get into some of the specifics of high-density designs, I want to take a look at some of the basic aspects of this design and how they conform to most manufacturing capabilities. So first, let's take a look at the surface layer. So here, if I just turn off the 3D models and we start scanning around the surface layer, we can see a few things that should be pretty obvious. So one of these is, of course, solder mask slivers. Now here in this region where I'm scrolling, we don't see any small slivers, but once we get over to here, we do see a small sliver right here in between this pad and this SMD pad. So this distance right here is very small, and this would normally trigger the design rule violation. Now, if we zoom out and flip over to the back side, we can see another couple areas where we have small clearances between solder mask openings and other areas of the design, or between two solder mask openings. Here you can see right here we have two open pads, and we have a very thin solder mask sliver between them. We also have pretty low clearance between, for example, this piece of silk screen and this opening on the solder mask. You do want to apply more clearance than that, or just delete these little silk screen bars. And those are some of the things that we would want to clean up in this design on the surface layer. You can see a couple other areas, for example, right here. This bar on the solder mask is really close to these open pads. And these are the kind of things that a manufacturer would send you an email about and ask you to correct. Now, some manufacturers might offer to do the correction themselves. That's fine, but of course, if you want to streamline your ordering process and avoid that back and forth with a manufacturer, and especially with an overseas manufacturer where that back and forth can take a few days, you just want to do this yourself and remove any of those violating pieces of silk screen, and then spread out these components a little bit more in order to make room for a larger solder mask sliver. Now, if we take a look at an example capability from a PCB manufacturer, you can see the order of magnitude of the solder mask sliver that you would need to have in a design. So let's go ahead and take a look here at this web page for advanced PCB. Now, I've shown this manufacturing capabilities page in another video, and what I really want to do quickly here is just scroll down to the solder mask web requirement section here in their capabilities list. So here we have solder mask web over laminate, or between the pads. And that's basically the situation that we're looking at right here in between the pads for these two components. So here you can see that they list a value, a minimum value of 4 mil for their standard process, 3 mil for their advanced process, and then 2 mil for their super advanced process. So if we go back here into the design rules for this design, And then we scroll down here to the minimum solder mask sliver rule. You can see here that the minimum solder mask sliver is set to less than 1 mil, so it's 0.787 mil. So this is one of those things, again, where a manufacturer is going to send you an email, and unfortunately, a manufacturer cannot just correct this for you without bringing the solder mask over the pads and making the pad size possibly too small to solder a component onto. So they're going to send this back to you and ask you to move those components to make space for a larger solder mask sliver. They might also just give you a warning and tell you, hey, this solder mask sliver might pop off, and it's in your best interest to move those components to prevent a potential defect. Now, another issue on the surface layer can be seen in this view, and you can see it right here on these two placements. Take a look at these two components. They have their pads very close to the board edge, and if we just do a really quick approximate measurement, we can see the distance that we're talking about. It's about 5 or 6 mil from the board edge to that copper on those SMD pads. Now, normally it's good advice given by manufacturers to pull back any copper elements by at least 10 mil. And that would just be for like copper pores. And if we're talking about actual components, they might tell you to pull it back more than 10 mil. So this is another thing where a manufacturer is going to send this back to you and ask you, the designer, to correct it. Now, maybe they don't send it back to you. Maybe they just give you a warning and they tell you, hey, when the board gets cut out of its panel, the route might cut into that SMD pad, and that's just a risk that you may have to accept. But generally, it is in your best interest to just move those components back a little bit and make a little bit of room to the board edge. Now, you can actually define this as a design rule if you just go into the Rules and Constraints editor, and you'll see here there is an entry for board outline clearance. Now here, when I open up this new board outline clearance rule, here you can use the default values here. You'll see that it's set to 10 mil. That's totally appropriate for pretty much every design. Now, of course, make sure to get your fabricator's capability list, check what it says about pullback from the board edge. They might say 10 mil is fine. They might recommend up to 12 mil or even larger. Just make sure to check that with your manufacturer. And then the next thing I want to look at, since we're inside the design rules, is up here in the clearance section. Now here inside the clearance rules, you can see here that we have 3 different clearances. So here we have a clearance rule for some voltages, and then here we have a clearance rule which looks like a global clearance rule, and then we have another global clearance rule. Now here, because clearance 1 is on top of clearance 2 inside of this list, that means clearance 1 is going to take priority. And you can always adjust the priorities in this priorities dialog. And so it's going to define which of these rules takes precedence. Now you can see here that the clearance 2 rule is not enabled, and it's set to 0.1 millimeter or 4 mils. Now here, the clearance 1 rule sets the clearance all the way down to 2.8 mil. Now that's a pretty aggressive clearance value. Now if we just take a look at advanced PCB's capabilities again, and we scroll up to the top, we can see here that we have a clearance requirement as a function of the weight that gets etched in the PCB on the surface layers and on the inner layers. So the minimum spacing value depends on 2 factors. One of them is the copper weight that's being etched, and then the other is whether you're on an inner layer or an outer layer. So here you can see what those values are. So here, for example, if we have 1/2 ounce copper on an inner layer, you can see here that you don't get down to 2.8 mil or lower until you're in their advanced process. The standard process sets it at 3.5 mil. Now, if you're on the outer layer, it's even larger. Here you can see with the 1/2 ounce copper base, you can see that this is 4.5 mil on the outer layer, and then it's at 3 mil on the inner layer. And it doesn't get down below 3 mil until you go to their super advanced process. So I bring this up to highlight 2 points. First is that if you're going to use heavier copper or a more standard copper value, for example, in a traditional build, you can't make the clearances too small. The reason is that the board may not be manufacturable and it might get no bid, or at minimum, the manufacturer will send it back to you and ask you to correct it. However, if you start with lighter copper on the outer layer, for example, 1/4 ounce or 3/8 ounce as your copper base, then you can get that clearance value down to a lower level. But that could be problematic, for example, if you have controlled impedance. If you have controlled impedance and your traces are sized to a particular width in order to hit an impedance target, going to thinner copper can then impact that impedance calculation and could put you outside of your allowed tolerance. This is why we need to define the copper weight inside the stack-up, and then when we create a mechanical drawing or when we create a fabrication drawing, we make sure to include that information in that drawing. So with that in mind, let's go ahead and take a look at the stack-up for this board. Now here we are inside the stack-up. You can see that this is a typical 4-layer board, except for the fact when you look at this central core layer. You can see here that the central core layer is only about 10 mil thick. And when you take a look at the total thickness, you will see that this board is only 25 mil thick. Now, I would recommend first making the total thickness 40 mil or 1 millimeter. So all you got to do is just beef up this central dielectric thickness. You can make it about 25 mil, and you can see here that this sets the total thickness up to about 40 mil or about 1 millimeter. The next thing that needs to happen in this design is we have to adjust the copper weights. So as I was mentioning earlier when we were looking at the manufacturer capabilities, we definitely want to change this to one of these thinner copper layers. So for example, you might use 1/2 ounce final copper thickness on the outer layers and then 1/4 ounce or possibly 1/2 ounce on the inner layers. Now 1/2 ounce is totally appropriate on the inner layers. On the outer layers, you might want to go with 1/4 ounce and then plate it up to the final thickness value once all of the through-hole vias are plated. So that's the copper weight that we want to use in the design, but then we want to look at the via types. Now, if we just go back to the PCB for a moment and put this into 2D, we can see here, if we just scroll around, that we do have a lot of vias in this design that are blind vias. But you can see here that we have something interesting. We have via transitions from 1 to 2, and then from 1 to 3, which are just standard blind vias. So this assumes or implies that these are all mechanically drilled. But then if we go down to the bottom layer, you can see that we have blind via transitions going from 4 to 3 and then from 4 to 2. So you can see that right here in this part of the design. Now, if you know anything about mechanically drilled blind vias and mechanically drilled buried vias, you will know that you cannot have crossing or overlapping blind vias like this because they cannot be manufactured. So we already have that right here in this view. Here you can see that this one goes from layer 1 to layer 3, and then this one goes from layer 4 to layer 2. So they basically cross over each other. So that will not be manufacturable with a mechanical drilling process. So just going back into the stack-up, if we click on the via types tab, we can see all of the different via spans that are defined in this PCB. And you can see here that we have those overlapping blind via structures, and then we also have some blind via structures that start and end on the same layer. So those are also not manufacturable. So in conclusion, none of these blind vias as they're defined here are manufacturable, but I know why this was done. The intention here was to be able to define any blind via span that you want in this design without having to actually manually place blind vias from one layer to another. Unfortunately, in order to get the correct NC drill data out of this design and into your manufacturing files, you can't define these vias as groups. The reason is that these layers are going to be drilled individually, and then they're going to be laminated on top of each other in order to form the full stack-up. So you can't have these overlapping drills defined separately if you want to have blind vias between each of these layers. So what we have to do is redefine all of these vias. So what I would do is I would just go back and delete all of these vias, and what we should do is instead have a buried via going from layer 2 to 3, and then we should use microvias on the outer layer. So we should have a microvia from layer 1 to 2, and then we should have that same microvia from 3 to 4. Now with this type of via definition in this design, you could actually route from layer 1 to layer 3, or from layer 4 to layer 2, or any of these other combinations that we see in the PCB layout, and it will actually be manufacturable. Now the only difference here is in the manufacturing process. Here these outer layers are going to be manufactured with laser drilling, And if you're going to be picking your own materials to appear in this stack up, you need to make sure that the dielectric that you use on those outer layers is compatible with laser drilling. So if you're ever looking through materials data sheets, you will see different types of materials that are often marketed for example, high density designs. And oftentimes they will just state whether or not they are compatible with laser drilling right there in the data sheet. Now, what about the core layer? Well, you can see here that we've defined a mechanical drill from layer 2 to layer 3, so we don't have any laser drilling happening in that core layer. So we don't need to worry about getting a laser drillable core or a laser drillable compatible material. We can just use a standard core material. Now, if we're going to be using microvias on the outer layers, how does that impact the thickness of this outer prepreg that we would use in this design? Well, we can use this 3 mil thick prepreg if we want. We just need to make sure that the vias are sized large enough to fit within the aspect ratio requirement imposed by the fabrication capability. So typically that maximum aspect ratio is probably going to be something like 0.8 to 1. And at the very, very maximum, you might see an allowance for a 1-to-1 aspect ratio on the outer layer. So that means about a 4 mil drill is going to be your minimum allowed drill size in these outer layers if you use a 3 mil thick prepreg. Now I'm going to close out the stack up without saving it so that way we don't mess up any of the existing routing, but let's take a look at the existing blind vias in this design and see if those will be compatible with the aspect ratio limit that I just mentioned. So here, if we go back to the top layer, you can see here that we have some vias going from layer 1 to layer 2, and let's just click on one of those vias. So here you can see that the hole size is 6 mil. So this is my other clue that this is intended for mechanical drilling and not for laser drilling. But regardless, if you were to define this via as a microvia based on the aspect ratio limit that I just mentioned earlier, you could use a 6 mil drill diameter with laser drilling. That would basically set the whole aspect ratio to 0.5 to 1. So that's going to be within the aspect ratio limit, and any fabricator on the planet that has laser drilling capabilities is going to be able to manufacture that board. So Amir, if you plan to do an update on this design, I would highly encourage you to take a look at the vias and implement the stack up that I showed in this video. And if you do it, send it to me and we'll review it again on the channel. Now, the last thing I want to go over in this design actually doesn't really relate to high density designs specifically. What I actually want to look at is what's going on with this grounding strategy. Now here, the astute viewer will notice that we have different ground nets. You can see here that we have an AGND ground net, and then here we have a regular GND ground net. So we have an analog ground and we have a digital ground, and you all know exactly how I feel about that.
Stop it. Get some help.
Now, most of the time I tell people to not do this, and for good reason, but if you do it and you have to tie the grounds back together, normally you would do this with a net tie. And the net tie is just a simple component that, well, shorts two nets together without creating an error in the IPC netlist analysis that's done in CAM software. Now, a net tie would normally just be applied here at the boundary between these two nets. But here, we don't actually see a net tie. Here we have a copper region that shorts these two things together. So what I would recommend, first thing you do is, if you are going to have a connection between two different ground nets like this, create a net tie component. That way you don't create a short circuit error inside of any CAM tool that then analyzes the netlist output when you create your manufacturing files. Now, why do we want to avoid doing this? Well, you can see here that we have this split basically traveling through the most of the design, and if we just scan through the different layers here, you'll see that there are multiple opportunities for traces to cross that split. So you can see here, I'm just highlighting a few of these underneath this component, and those traces are all at or near that split and crossing right over them. So here, if I go to layer 3, you can already see where some of those traces are located. So the first reason we don't want to do this, first, if any of these traces are carrying digital signals and they travel over this split, then you're going to have a nice big radiator. They're basically going to emit a lot of noise, and that could cause you to fail radiated emissions testing. The next reason is much easier to understand when we look at, for example, this switching node path. Here you can see that we have this switching node path crossing the boundary between these two regions. And what that's going to do is it's going to create a huge return current path that goes basically all the way around the center to the right edge of the board. Now this SW line is part of a switching regulator, as you can see here on the top layer. Now even though this return current path passes over a lot of solid copper on the top side and the bottom side, the problem is that the return current loop that you trace out around this board is huge, and that gives it a lot of opportunity to radiate noise. Even if the edge rate isn't very high, this could create a radiated emissions problem that also causes you to fail radiated EMI testing. Now, of course, it's possible that these lines are just carrying DC current, or maybe they're low-speed digital, and you don't have any problems with radiated emission. But what if this design needs to pass susceptibility testing? Well, having these big splits that span under all these lines on the top and bottom and internal layers is going to reduce your immunity to external sources of EMI, and that is going to increase the chances that you fail susceptibility testing. Now, if these are digital lines, it also creates the potential for crosstalk between these regions where there's basically no ground. You can have much higher crosstalk in these regions where these traces are close to each other compared to these other regions where these traces are over a solid region of ground. Now, I'm sure someone that's watching this will say, well, hey, this is an audio design and we actually need to do this so that we can control the return current path associated with those audio signals. However, the placement has already taken care of that for us. If you notice here on the left, we have a BGA, and this is a BGA for an NRF53 microcontroller. Now notice how it's placed all the way over here on the left side of the board where it's far away from any of the audio signals. All the audio signals are located over here on the right side of the board, and just putting distance in between those different groups of components is enough to prevent the audio signals from being corrupted by any of the digital stuff elsewhere on the board. So this is yet another example where we've put this split in between these planes, but we really don't need it, and really the smart thing to do is to just use solid planes everywhere in the design with a single ground net. Thank you, Amir, for sending us this great design. I was very happy to review it, and there are a lot of learning opportunities in this design. So if you ever give this design an update, make sure to send me a message on LinkedIn with the updated design files, and we'll give it another review on the channel. To everybody else that's watching, thank you so much for watching the video. Make sure to hit that like button, hit the subscribe button, leave your comments and questions in the comment section, and don't forget to call your HDI fabricator folks. We'll see you next time.